Good, so welcome, and thanks for having me. So I was trying to work out a large Fibonacci number. You might wonder why. Well, just because, just for fun. And you can see here, if you look at the graph, this is my laptop. So I've got 4 cores, and it's hyper-threaded. So you've got basically 8. It shows like there's 8 cores, not actually 8 cores. And I played around with it a bit, and I added the ManagedBlocker, and I got to the following picture. Now, there's a lot of green, a bit of black, not too much red, which is good. And if you look at the beginning, you notice at the beginning there was a fair amount of black before we really started going. So the initial startup with the regular Fibonacci calculation was quite a bit of black over here. And once I added the ManagedBlocker, it went away mostly. So I'm managing to get better utilization at the beginning of my run. So what we're going to look at here is how we got there. And I'm going to use this calculation that people know. You probably all know about this Fibonacci. F of 0 is 0, f of 1 is 1, and f of n is equal to the previous 2 numbers added together. Now, did you know that the JVM has an implementation of Fibonacci? Did you know that? Who knew that? Did anybody know that Hotspot has implementation of Fibonacci? Now, you look very surprised. You should be surprised. You should be very surprised. So let's say that I want to try this out. And let's say that I want to say, hello world. There's a class called hello world in sun.jvm.hotspot. And it's got a method called Fibonacci. Right? Believe it or not, it's there, right? And if you look at it, it's like the worst possible implementation you could make, plus it's not actually correct, right? Because if n is 0, it's supposed to give back 0, not 1. Right? So it's an exponential time complexity algorithm, and it's wrong, right? So let's get back to our code, because the problem with this algorithm is that the numbers get large very quickly. It's a bit like the Australian rabbit population, which just grew like rabbits do. So if you implement this using a very naive implementation of just saying if n is less equal to 1, they return n, otherwise return basically what they did in the JVM, in the hotspot, then you have very, very poor time complexity. We could do this with an iterative algorithm, which gets away from the recursion, but we still have problems with this algorithm because the number overflows round about Fibonacci 93. So the lower 64 bits of the number are correct, but not the rest, so it doesn't really help us. But you can get Fibonacci 1 billion on my laptop in about 400 milliseconds, so that's quite fast. But the moment that you make it with big integer, the add function of big integer is also linear. So you've got a linear multiplied by a linear, and you end up with quadratic, and you can't work out such big numbers with this mechanism. The third attempt is with Dijkstra's sum of squares. Now, this has much better time complexity because at every step, we divide the number by 2. So we halve and halve and halve. You end up with logarithmic time complexity of the actual calculation algorithm. Now, originally in Java 7 and before that, the big integer multiply was also a quadratic multiplication. So multiply was really slow, order n squared. They fixed that in Java 8 for big numbers. If you go above a certain threshold, then they use something called Karatsuba, which has a better time complexity. And if you go even bigger than that, then they use something called Tomb Cook, 3-way Tomb Cook, which is n to the power of 1.465. But only if it's bigger, because there is a lot of setup cost to use that particular algorithm. Now, it's still single-threaded, and we will make some adjustments a bit later. Now, here's the algorithm. Let's implement this in Java. So what I want to do is to have f of 2, if it's odd, I want to have one calculation. If it's even, I want a different calculation. Unfortunately, Java doesn't have operator overloading, so we have to write some code which is a bit ugly. Now this at the moment, let me just delete this. nonsense class. This at the moment is a very slow algorithm. And if I did an estimate that if I tried to work out Fibonacci 1000 with this algorithm, it would take approximately 10 to the 200 years, right? Which is a very long time, and we won't be able to get through that today. Right? I've got 45 minutes, so I've got only 35 minutes left on that. 25 left. So we won't have time for that. And that's because of the time complexity. Now, let's rewrite that, and let's say that, first of all, we say int half equals n plus 1 divided by 2, and then if we then work out the big integer f naught equals f of half minus 1, and f of 1 is f of half, and then we combine the two. So we can say if n was odd, then we're going to say return f naught dot multiply f naught. This is actually a square method, but it's not public, so we can't call that. Add f1 dot multiply f1, like so. Else, what we do is we say return, and if you look at the algorithm, it's f the first one, f naught times 2, so we can say f naught dot shift left by 1, which is the same as multiply by 2, then we add f1 to that and multiply the result with f1, like so. So this will now use a better algorithm. And what we're going to do here is we're going to run this and see whether it's faster than 10 to the 200 years. Hopefully it will be a bit faster than that. So let's run that. And where's our Fibonacci test? So here's a Fibonacci test. This tests that the code works. Also prints out the time it takes to run this test. And Fibonacci 1000 now takes 3 milliseconds instead of 10 to the 200 years. So that is already a slight improvement. And normally when you try to make code faster, you're going to get much more benefit from improving your algorithm and your design than from trying to brute force parallelize everything. So always keep that in mind. Oh, you can update the IDE. I don't want to do that now. I'll do that later. So it's taken a while to work out Fibonacci 100 million, but remember the number is a very large number. So it would take a while. So it took 37 seconds to do that. So let's write that down, and we have achieved something already, which is great. So we're going to just write this as our very first step. Right, now that's all great, but what is the utilization of this code? And if you run the code at the same time whilst running top, you'll see, you won't see anything because it's too big. There's Java. So you can see Java is running at 100% CPU. So it's obviously just a single-threaded process. I haven't done any multi-threading here. So what we want to do as a first step is to try and parallelize this a little bit. We're going to do that by updating by creating a recursive task, and by forking that, and that recursive task is then going to be joined again afterwards. So by forking it, we're allowing it to run in the common fork join pool. All right. So here's what we're going to do: is we're going to type this code in. So I'm going to just hop over here and go back to my code, and the first integer I'm going to make with the recursive task. So big integer over here, and f naught task equals new recursive task, and then we're going to say return f of half minus 1. So the same calculation that we had down here, we're now doing inside the compute function, like so. After we have created the task, we say f naught task dot fork, and if I currently am inside a fork join thread, I'm going to use that fork join pool. Otherwise, I'm going to launch inside the common pool. And then once I've done that, I can say f naught task dot join. So join with what I forked before. So now I've got 4 cores running, 4 effective cores. I've got hyper-threading, but it's really only 4 cores. So before it took 37 seconds to run this code, how long do you think it will take now to run this code? So 37 seconds and 4 cores. What do you expect? 12 seconds. Okay, great. Let's try it out. I don't know. So let's see. You're pessimistic, very pessimistic to say 12 seconds. You would expect to be like 9 seconds because it's a quarter, right? We've got 4 cores. And it's running, and it's running, and it's running, and it's running. And it's not really, it's really gone past our 12 seconds. And if you look at at the CPU, it was running at 100%, right? So the output here, if you look at the output, is 21 seconds. So it is faster, but it's not 4 times faster. It's not even 3 times faster. So that's, of course, the problem here. Oh, that's funny. What's that all about? So this is after we've done a bit of work. And if you run the code, you'll see what happens if you run the code, because at the beginning, we are running at like hundreds of percents of CPU, 400% CPU. And then it goes out to 300% CPU, and eventually 200% CPU, and then the longest time is 100% CPU. Right? And the reason why we get this is because this is a recursive decomposition, a divide and conquer algorithm, where I'm taking a big problem, I'm dividing it in half, dividing it in half, dividing it in half, and that's easy, but then I've got to merge them all together again. And we're spending a lot of time in the final merge because it's a very big final calculation. So we managed to do something, but we haven't gone far enough. All right. So what we need to do is to make big integer also parallel. Now, big integer at the moment is not parallel. It is single-threaded. And there are 2 algorithms that we could look at. One is Tum-Cook, other one is the Karatsuba. The Karatsuba is if it's above a certain threshold, but if it's even bigger, we use Tum-Cook. So the one we want to look at is Tum-Cook. Now, I have done this hack a few times already, and I don't understand how Tum-Cook works. Right? I want to just this disclaimer. I do understand how Karatsuba works, but I don't understand how Tum-Cook works. So I'm going to hack it without understanding at all how it works. Right? That's the point, to be able to parallelize something without understanding it. Now, I'm using Java 8 for the reason that it's easier to hack than Java 9. You can also hack Java 9, but it requires 3 steps instead of a single step. I have to create a patch for the module, and then I have to insert the patch, and it's a whole bunch of things. Whereas in Java 8, you just add it to the boot class path, and it's much easier. So let's do that. What we do is we go back to our code. Let's close this. Go back to our code, and we select the big integer, copy, and then we go to our project, and we've got a separate module so that I don't violate any license agreements, and I paste it in there. So if you get paid by lines of code in your work, this is how you do it, right? This is how you get a bonus. I've just created like a few thousand lines of code. Brilliant. Now, that's all fine and well, copying and pasting the integer in there, but how do I actually use it? Well, let's make a static block and just make sure that it's actually being called. Hello, Voxxed days, Thessa, oh no, wait, where are we? Oh, it's Athens, sorry, Athens, sorry. I knew I got it wrong. It's much too hot here. Now, if I run this code, you won't see that pop out, right? Because, well, I'm using the normal big integer. You don't see any hello, Voxxed days. But when you run the code, you can specify that you want to use that particular big integer. So you say here, boot class path /p, which is, prepend, not append, /a is append, this is /p, which is prepend. So we're going to prepend this to my boot class path, which is the JDK, JVM path, where all the classes are that the JVM. So if you want to replace, for example, Java lang string, or I don't know, that won't necessarily work so well, but you could do it like this. And let's run this again and see now. There you go. Hello, Voxxed Athens, right? That's popped out of the big integer. So now we know we're using this big integer. And now we're going to hack the multiply method, multiply to cook. We're going to hack this one to be parallelized. As I said, I don't know how this works. There's a whole bunch of mathematics. I'm too stupid to understand this stuff. But I do know that I want to make multiply parallel. I do know that part. So I want to make this parallel. And what I'm going to do is I'm going to fork the first multiply. Then I'm going to do the next multiply in my current thread. Then I'm going to fork the next multiply. And then I'm going to work out the other multipliers and then join the second fork again. So I always want to join before I do another fork. And in some versions of Java, if you don't do it that way, you can get a thread explosion and end up with an out-of-memory error from too many threads. So I always want to join again before I do the next fork. It's assumed that you're doing that. If you don't do it, things are not very happy. So we need to have a multiply task, which we need to create now, which is going to be the v0 task equals new multiply task of a0 and b0. Right? So let's create this as an inner class. Create inner class multiply task. This multiply task is going to be a recursive task again, so extends recursive task of big integer, and it needs a constructor. So let's go back and add this constructor with a and b. It's going to be a, just plain a, and b, like so. Let's add fields for those, a and b. And then we are going to also have inside here something has gone wrong here. I think it's deleted no, that's in the wrong place. Something's desperately wrong here. Okay, we also need the method compute, which is going to simply return a.multiply b. A.multiply b, like so. Okay. Now, whilst we're here, right, I'm busy breaking big integer. You know that it also has a square method, big integer. Right, it also has a square. So there is a square method, but it's private. Now, we could also make this public if we wanted to, right? But I'll leave it like this for now. So here's my multiply task. Let's go back. And I create my task. I then fork it, so f0 task.fork. And then I do the second multiply, which is over here. And before I do the third multiply, I say v0 equals v0 task dot join. So I need to be very deliberate in the way that I do this. I'm going to do the same with dA1 times dB1. So it's going to be a multiply task is v1 task equals new multiply task with dA1 comma dB1. And then we're going to say again v1 task, v1 task, I'm getting this right, dot fork. And before and after I've done all my other multipliers, I'm going to say v task dot join, like so. It's very awkward typing like this. So this is now going to parallelize the multiplication. So even though I don't know how this algorithm works, I'm doing a divide and conquer. I'm doing a parallel recursive decomposition, which is fantastic. Let's go and make the square task as well. It's going to look very similar. Square task is going to look like this. Square task equals new recursive task with a single big integer. Let's have a new constructor constructed for us. And then this is going to just say square. Okay, so this is my square task. And I'm going to hack this into the square term cook. It's going to do that too. And over here we're going to make a square task of v0 task equals new square task of a0. Okay. And then I'm going to say, after that, I'm going to say v0 task.fork again. So I fork it, And then before I do the third square, I'm going to join with the one that I did before. So v0 task dot join. So that's great. And then I'm going to do the same thing with the v1. I'm going to say square task v1 task equals new square task da1. And then I'm going to say v1 task dot fork. And afterwards, once I've done the other squares, I'm going to say v1 equals v1 task dot join. So v1 task dot join. There we go. Now, now I'm really going to do the calculations in parallel. And we should see a slight improvement in our performance now. Oh, I'll switch it. Run at the same time. Show you this. So this is now my top, and you can see that we're running, and we're running at about 400%, which is what we really want to do, running at 400%. And before we were about 20 seconds, now we have gone back to, or down to a more respectable number, to 16 seconds. We're still not at the one that you said earlier on, of 12 seconds, but we're getting faster, right? And of course there's Amdahl. We can always blame Amdahl for everything. If anything goes wrong, it's Amdahl's fault. It's his fault. He made the law, it's his fault. So there we go. Let's stick this in here. And not in here, but put it into the Fibonacci. Remember how we're doing here. So this is now time is 16 seconds, from 37 down to 16 seconds. And we are using all the resources we've got. Now, this is all fine, but what happens if you run this on a bigger server, right? What happens then? So, I don't know if this is going to work as well. I set this up this morning, and it should work, but I don't know if it's going to work, so we'll have to just try. So what I'm going to do is going to push this into my GitHub. So git commit -a demo, git push, and then we're going to pull it onto my server. Now this is a server which Oracle has very kindly let me play with. They don't know what they got into there, because it's a 52-core beast with like 700 gigabytes of memory that I can just go and abuse for a few days. But here's our turbocharged Athens, and let's pull the latest source code from there. Now I need to just make sure that this is set up correctly. I think it should be, because I've got prepend. I've set the parallelism to 51 because I've got 52 cores. And now we're going to see how fast this is. So it's hopefully it's going to work. It also recompiles the code, and it runs. And before it was 16 seconds, now, well, it's not using all the available cores, right? Because Amdahl, right? We can always blame Amdahl for everything. In fact, I don't know if it's even working at all. I think I might have. Oh, yes, I know what the problem is. So the problem is that when I did the commit, I don't think I included big integer. So let's go back and just do git status. Yeah, that's what I did. Git add mathhack big integer. Git commit -a. I always do this. Forgot the bi. Git push. And let's try that again, and hopefully it'll be a bit quicker. Now, of course, having lots of cores doesn't help you if you don't have if you are, okay, that got replaced, and let's run it. Doesn't always help you, but it should be a bit faster than 16 seconds, right? I'm obviously not using all the available hardware. So I got down to 5.5 seconds. So taking my little laptop and replacing it with a 52-core monster helps us a little bit, but not that much, right? I can probably buy like a new laptop once a day with that machine cost. All right, so there we go, 5.5 seconds. What's interesting about here, if you look at the output here, it was 5.8 seconds of real time, wall clock time, but 2.5 minutes of processing time. So there we go. Lots of fun. Let's get back to reality. Now, unfortunately, something went slightly wrong with the timing this afternoon. And I've got something which expired 10 minutes ago. So it's not going to work, right? I will actually fix that, but I'll fix it once the talk is done. So if you want to write down this URL, you'll get a 90% discount on my data structures course. And I will extend it till 6 o'clock this evening, right? But at the moment, if you go to that image, you're going to get to like the 100%, no, to the 0% discount price, which is not going to work. So bear with me. I will fix it at the end quickly, and you'll get that. Okay. Now, one of the interesting things here is that we actually are calculating the same numbers down the two search paths, search trees. So you can see here that I'm working out, for example, Fibonacci 250,000. If I want to work out Fibonacci 1 million, I'm going to work out Fibonacci 250,000 twice. I'm going to work out Fibonacci 31,250 16 times, and so on. The further down you go down the tree, the more repetitive work you're going to do. So why don't we cache some of these numbers? So this is now the fourth demo. And with the fourth demo, what we're going to do is we're going to cache them, but we have to be careful with the cache because, number one, we don't want to have a memory leak. We don't want a memory leak. So we don't want to store a static map. Also, a static map would quite often give you a false sense of speed. It tells you that it's really fast, whereas it just got the value back from the cache. So we want to avoid that. So no static maps, and also be careful about concurrency because, of course, lots of threads will now be looking inside this cache whether the element is there or not. Now, before I run that, I want to run one more test on my machine. We'll stick with my machine for now. And that is my run. And I want to time what my CPU time is. Oh, sorry, I need Java 8 on here. I want to time up what my CPU time is and what my elapsed time is. Because we saw elapsed time was about 16 seconds. And we want to see what the CPU time is. So the CPU time should be right about 4 times that. So we can see now I thought 14 seconds. So it's a bit unpredictable. I thought I had time here. Let's do that again. So I'm expecting it to be about approximately 4 times, maybe 3 times as much CPU time as you've got elapsed time. Of course, you've got hyper-threading, so maybe it'll be more, but I've only got 4 threads running, so it should be round about there. And you can see here that you've got 16 seconds. Okay, user time is 1 minute, so it's a bit more. It's basically, it's about right. It's about 4 times as much, roughly 4 times, because it's of course 60 seconds is 1 minute, so it's about 4 times as much. And so that's my real-time user time. So I'm using up a lot of CPU cycles here. Let's add the cache and see how this helps. So if we go to the cache, I'm going to now have inside here 2 methods, one calling f of n, other one calling f of n, which is going to be a private method, which also takes a cache. So it's going to be a map of integer to big integer, like so. And that's going to be my cache of values. Okay. Now the cache is going to be set up. First of all, this check I don't need to every single time. I'm going to put this up here. I'm going to make a cache up here, map of integer, comma big integer, cache equals new concurrent hash map, very important. And a tip that I'd like to give you is don't ever use hash map. Always use concurrent hash map, right? Even if you don't need concurrent hash map, don't use hash map. Use concurrent hash map in your code. There are good reasons for it. So cache.put 0, 0 and cache.put 1, 1. Okay. And then we're going to say return f of n, the cache, right? So the cache inside the F method, I need to now check whether I've got that already. So I need to say cache.get of n result. And then I can say if results is null, then I'm going to calculate it. And then I'm going to, here when I saw f, I'm going to say f of half comma cache, and f half minus 1 comma cache as well. So I'm going to obviously use that within my calculation. Afterwards, once I'm done, I throw away that cache. I don't want to have a memory leak. So what we now do is, instead of returning, I'm going to say result equals, and result equals, and then we have to say map.cache.put in comma the result. And then we have to say return the result. So now I'm caching the results. I'm not working them out over and over and over again. Let's run it again, and we'll see how we do. Class not found. That's funny. I'll try it again. What's going on here? I'll just run it from here. It should recompile it and run it. So this is now running, and we also want to see what the time is, not just the elapsed time, but the CPU time. And we expect it to be quite a bit faster, and it is a little bit faster, but not that much faster. And there's a good reason for it. You see, the problem is that if you look at the tree that we showed just now, we actually are working out the same values at the same time with multiple threads. Right? So we do get better. We got from 16 seconds down to 10 seconds, which of course is great. User time is 40 seconds, so it's a 1-to-4 ratio, is what we wanted. But we still are using a lot of time. So let's try something else. See, as I said, we're working out the same values because we're working out at the same time. So why don't we add a reserved caching scheme? And the way that works is we are saying that instead of getting the value, we say put if absent, and we take a special big integer that we pass in. And that is then used in order to be a placeholder. So then afterwards you can see if the placeholder is there, then somebody else is busy working with that number. All right, so let's do that. We make a private final big integer reserved equals, we'll make it dot value of minus 1,000, so it's not cached. And then whenever we say get, instead of saying get, we're going to say put if absent in comma reserved. All right? In comma reserved. And if it's null, then we were the first to put it in, because put if absent, if it comes back with null, then we were successful. So then we do the calculation. Otherwise, we put in otherwise, else if the result is equal to the reserved, then we know that somebody else is busy working at the moment, and now we need to wait for them to be finished. So we're going to say while result equals cache.get of n is still equal to reserved, we're going to wait on reserved. So we're going to say reserved.wait, and we're going to wrap this with a synchronized reserved. And if we get an exception over here, let's wrap this whole thing with the interrupted exception. Then we're going to simply throw a new cancellation exception, like so. All right. So this now will wait until we're done. And what we'll do is we'll do the same synchronized around the put. So we'll synchronize around that as well. And we'll say, after we've put it in, we'll say reserve.notify all. So anybody who knows about this or cares about it will get a notification that it's now available. Okay. Oh, wait, I must compile this, I must run this. So we run it, and we can now see that it runs runs nicely. And the interesting part here is that it actually, you can see it's a bit faster, right? It's 9.4 seconds instead of 10 seconds, but the user time has gone down quite a bit. What does that tell us? It tells us that the user is blocked waiting. So there are threads which are in the blocked state waiting for other threads to do their work. Okay? So I'm not utilizing all 4 of my cores. That's what I'm saying here. So how can we utilize them? This is where the final piece of the puzzle comes in. And then we'll take some questions. And that is the managed blocker. Now, the fork join pool, when you configure it, when you construct it, you specify the desired parallelism. And I've said I want to have 4 threads running at the same time. I want a parallelism of 4. But what happens is when I'm waiting, I don't get that 4 because I've got threads waiting for other threads. So what you do is you take this code over here, this waiting code, and you wrap this into a managed blocker. So it's very easy to do. Just private class reserved blocker implements the managed blocker, which is inside fork join pool. It's just an interface with 2 methods, is releasable and block. And I'm going to need these 3 fields. I'm going to have inside here a private, big integer result. And I need the map and these 2 parameters as well. So stick them in there as well. So it's going to be a semicolon. And let's make these private and private. Okay, these will be final as well, and they'll be set in the constructor. There we go. Here's a constructor. Is releasable is going to be this calculation over here. So that goes into is releasable, except it's going to be, if it's not equal to reserved, then it's releasable. So that is the condition we're waiting for. And then here I'm going to say, while not is releasable, wait, and then return true. So now we need to use this reserved blocker. We do it inside here. We say reserved blocker equals new reserved blocker. We pass in the n and the cache. And this will now wait until it's done. Now what's interesting about this reserved blocker is if you're not actually inside a fork join thread, it will just do the normal waiting. But if you are inside a fork join thread, it will actually possibly spawn off additional threads to keep our utilization high. So then I can say result equals blocker.result. After I say blocker., no, I must need to say fork join pool dot manage block the blocker. Right? So manage block the blocker will do the actual blocking. Okay, so let's run the test again and see what the utilization looks like. So run. We should be a bit faster than 9.4 seconds. Hope. 7.7 seconds. And we can see that the real time is about a quarter of my user time. So we're getting this factor 4 utilization, which is brilliant. And a little homework for you is to do this with Computable Future. So I've seen good solutions for that. Do try that. Send me your answer, heinz@javaspecialist.eu. And I've got time for maybe one question. If you're not on my newsletter, please subscribe. Inezopia, it's from Crete, Atachania, Kimenoro. Alicia, Choris Plaka. Yati Oichi. Okay, so
thank you, Heinz, for that awesome presentation. So guys, we're running a bit tight on schedule. So may I suggest you get 3 questions from Heinz, and instead of doing a coffee break, because we need to synchronize with the room next door, you grab a coffee on your way next door, okay? So 3 quick questions.
3, cool.
3 quick ones, come on.
There's a question.
There's one over there. Speak up, stand up.
concurrent hash map? Thank you. Why we should always use concurrent hash map instead of hash map?
Ah, that's a great question. Okay, the benefit, okay, the disadvantage of using a hash map is that you can get an infinite loop inside the hash map if you accidentally use it with multiple threads. Correct, Kirk? We had that problem. So we actually had to fix some of this code, and this happens very often, that you've got a hash map, you think that the hash map is actually never going to be used by multiple threads, but a hash map is a type of store that is quite commonly used by multiple threads. So the disadvantage of a normal hash map is that if you accidentally use it by multiple threads, you can end up with an infinite loop inside. There are very few disadvantages with using the concurrent hash map in terms of performance and size and so on. But this is only from Java 8. Prior to Java 8, the concurrent hash map used a lot more memory than the normal hash map. So this is why we recommend that we always use the concurrent hash map, just in case somebody accidentally uses it with multiple threads. There's very little disadvantage and a huge benefit to using it.
Thank you. Second question. Question over here. Yep.
Can you gain some precious milliseconds by initializing the initial size of the hash map depending because you know how many computation you will make?
Okay, so you want to improve the performance by setting up the concurrent hash map up front, or? I don't think that's your bottleneck. So I doubt that you actually notice it even. Kirk thinks it is. Pardon? Well, the hash map is actually not very big. The concurrent hash map doesn't have very many entries. For 100 million, it will probably have about 70 unique entries. So it's a small map. The entries inside are big. They're massive. But in fact, I don't even think it's going to be resized that often. Because what's the default concurrent hash map size? 16 or what? This works now, by the way, until 6:30.
And last question.
One more question.
No? Okay, so you can meet Heinz later on at the networking. So big round of applause, guys. Thank you very much.